Welcome back to the Deep Dive. Today we're not just talking about a dinosaur. We are talking about, well, I think it's fair to say we're talking about the dinosaur.
Right.
And I really don't say that lightly.
No, you're absolutely right. It really is the definitive article, isn't it? It holds a special place.
It really does. I was thinking about this on the way in.
Mm-hmm.
If you walk into any kindergarten classroom, pretty much anywhere in the world, and you ask a 5-year-old to draw a dinosaur,
Mm-hmm.
what are they going to draw?
Mm.
They're going to draw one of two things. It's either going to be a Tyrannosaurus Rex, big teeth, tiny little arms, or
Be this one. The one with the 3 horns and the big shield on its head.
exactly. We are talking about Triceratops. And I feel like everyone listening right now has a very, very specific image in their head. It's probably a plastic toy you had when you were growing up.
Oh, for sure.
Maybe it was from a certain movie franchise set on an island. It's that toy box version of the animal.
Which is a great starting point. I mean, it's iconic for a reason. But the
Mhm.
reality of this animal is it's just so much stranger, so much more dynamic, and frankly, so much more terrifying than that static little plastic toy.
That is exactly the mission today. We're going to take that toy box version and, well, we're going to upgrade it. We're going to look at the sources. And we have a huge stack today from the original 19th century descriptions to some really cutting-edge papers from the last couple of years. And we're going to find out that this animal was a marvel of social complexity, a biological shapeshifter, and maybe, just maybe, a little bit bristly.
And we absolutely have to talk about cowboys.
We absolutely have to talk about cowboys. I teased that. And I promise we will get to the Wild West.
Yeah.
But before we get to the lassos and the ranchers, let's just ground ourselves in the name.
Yeah.
Because it's one of the few scientific names that the general public actually knows and, uses correctly.
It is, yeah. It's a linguistic masterpiece, really. It's derived straight from ancient Greek. You have tri, which means 3.
Right.
You have kieros, which means horn.
Okay. And then you have empums, meaning face.
Triceratops.
Literally. 3-horned face. It's so elegant, so descriptive, it's perfect. It doesn't require a degree in Latin to get the picture in your head. You hear the name and you see the animal.
It is perfect branding. But here's the so what question to kick us off. Why does this specific dinosaur matter so much? I mean, aside from being incredibly cool looking on a lunchbox.
Well, scientifically, it is. It's foundational. It's incredibly important. In phylogenetic taxonomy, that's the science of how we classify organisms based on their evolutionary relationships. Triceratops is actually used as a reference point, as a pillar to define what a dinosaur is.
Wait, really? Say more about that. It's the standard unit.
Basically, yes. The clade, or the group that we call Dinosauria, it's technically defined as all descendants of the most recent common ancestor of Triceratops and modern birds.
That is heavy. So it's not just a random participant in the group. It's one of the 2 pillars that holds up the entire definition. Precisely. If you aren't related to Triceratops or birds in that specific way, by that definition, you aren't a dinosaur. So in a very real technical sense, Triceratops anchors the entire family tree.
And beyond that, historically, it's significant because of when it lived, right? It's right at the very, very end.
Exactly right. It was one of the very last non-avian dinosaurs standing. It lived at the end of the Maastrichtian age from about 68 to 66 million years ago. So it was there right up until the asteroid hit.
No.
If you could go back in time and stand on the ground on that final day, just before the impact, and look up at the sky, the animal standing next to you in that forest was very, very likely a Triceratops.
Talk about witnessing the end of an era. It's the final boss of the Cretaceous.
In many ways, yes. It was the culmination of 150 million years of dinosaur evolution.
Okay, so we know what it is. We know why it matters. But I want to go back to when we didn't know what it was. Because the discovery story of Triceratops is, well, it's a comedy of errors. It's almost unbelievable.
It really is. And it highlights something so important about paleontology. Even the absolute best experts, the giants of the field, can get it completely wrong if they don't have the whole picture.
So let's set the scene. It's 1887. We are deep in the American West. The bone wars are raging.
Oh, absolutely. This is the peak of the rivalry between Othniel Charles Marsh and Edward Drinker Cope. They're sending teams out all over the West, trying to one-up each other, naming new species as fast as they can dig them up. It's a frantic, competitive time.
And into this scene walks a geologist named George Lyman Cannon. He's working near Denver, Colorado.
Right. And you have to picture Denver in 1887. It's not the metropolis it is today. This was a rugged country.
Yeah.
And Cannon is out there doing his geology work, and he finds a fossil.
Not a whole skeleton, I'm guessing.
No, and that's the entire problem. It's just a pair of large brow horns,
Okay.
the ones over the eyes, and they're attached to a fragment of the skull roof. It's just the very top of a head.
Okay. So he wraps them up, puts them in a crate, and sends them off to the expert.
He sends them to Othniel Charles Marsh, and we have to contextualize Marsh. This man was at Yale. He was one of the titans of early American paleontology. He's the guy who named Stegosaurus, Apatosaurus, Allosaurus. If anyone in the world should know a dinosaur when they see one, it's O.C. Marsh.
So Marsh gets this crate, he opens it up, he sees two massive bone horns. What goes through his mind? What's his process?
Well, he looks at the horns, for sure, but more importantly, he looks at the notes on the geology. The person who sent it noted the rock formation it came from. Marsh, based on what he knew at the time, assumes that formation is from the Pliocene epoch.
And for those of us who don't have the geologic timescale tattooed on our arms, what does Pliocene mean in this context?
It means relatively recent, geologically speaking. We're talking a few million years ago. Crucially, this is long, long after the dinosaurs went extinct.
So right off the bat, he's ruling out dinosaur. He thinks he's looking at a mammal.
Exactly. He thinks these aren't dinosaur fossils at all. He concludes they must belong to some kind of giant extinct species of bison. Bison? Yes. He formally describes it and names it Bison alticornis, which means the high-horned bison.
That is just fantastic. So the very first Triceratops fossils ever cataloged were put in the books as a type of cow.
A very large, very strange cow. But, to be fair to Marsh, if you just saw those two brow horns in isolation, which are made of bone, and probably looked a bit like the bony cores of modern cattle horns, and you were told the rocks they came from are only a few million years old, a giant bison isn't an absurd conclusion.
Well, I guess that's convergent evolution, where different animals evolve similar shapes.
Precisely. But the universe wasn't done messing with them yet. Because the next big find, and this is my absolute favorite part of the whole story, involves a literal cowboy. This is the story of Edmund B. Wilson in 1888.
1888, so a year later. We're in Wyoming now, and Edmund is a cowboy. He's not a scientist, not a geologist. He's presumably out there on horseback checking fences or looking for stray cattle. And he's riding along a ravine, minding his own business, and he sees something.
He sees a monstrous skull, as it was later described, poking out of the side of the ravine. Now, you have to try and imagine that. You're on a horse, miles from civilization. You've probably never seen a dinosaur skeleton in a museum because they barely existed yet. And a skull the size of a small car is staring at you from out of the dirt.
It must have been. I mean, terrifying, or at least deeply confusing. What would you even think that was? A dragon?
Who knows? And Edmund, being a practical man of the West, decides he wants to retrieve it. Maybe he thinks it's worth money. Maybe he just wants the world's greatest trophy for the ranch house. But he doesn't have a rock hammer. He doesn't have plaster jackets.
He has a rope.
He has a lasso.
This is the most American scientific method I have ever heard of. I'm going to lasso the science out of the ground.
It really is. The story goes that he throws his lasso around one of the horns. He ties the other end to the horn of his saddle, and he spurs his horse. He tries to yank this massive fossil out of the cliff face by brute force.
And I'm guessing physics happens.
Physics happens. The fossilized horn, which is essentially rock, snaps right off.
Oh, that hurts my soul. Every museum curator listening just had a physical cringe reaction.
And to make it worse, the jolt of the horn breaking off causes the rest of the massive skull to tumble down into the cleft of the ravine, out of reach. But Wilson, he has the horn, he takes that broken piece, rides back to the ranch, and shows it to his boss.
And his boss is the connection, right?
Yes. His boss is a rancher and an amateur fossil collector named Charles Arthur Guernsey. And Guernsey, thankfully, knows who to call. He shows the horn to a man named John Bell Hatcher.
And we need to put a pin in Hatcher. He's a major character in this story.
He is the fossil hunter's fossil hunter. If Marsh is the academic general back at Yale, Hatcher is the guy on the front lines, the Indiana Jones of this whole operation. He was unbelievably tough and had an incredible eye for finding fossils.
So Hatcher sees this horn, and what does he think? Does he think bison?
No way. Hatcher sees this horn, and he knows immediately this isn't a mammal. He knows this is something reptilian and something enormous. He gets Guernsey to take him out to the ravine. He manages to recover the skull. This very skull becomes the holotype, the defining specimen, YPM 1820, and he sends it to Marsh back at Yale.
Okay, so now Marsh has a complete monstrous skull with a beak with giant brow horns. Surely now, he says, okay, definitely not a bison.
Well, partially. He immediately realizes it's a reptile. He recognizes it as belonging to a group he had named earlier based on fragments, ceratops. So he initially calls it Ceratops horridus. But then, as his team is cleaning the skull up, they find something Marsh hadn't seen before, a third horn.
The nose horn.
The nose horn, in Triceratops.
Oh, so that's the final piece of the puzzle.
Exactly. That third horn on the nose convinces Marsh this is a whole new genus, distinct from Ceratops.
Right.
He renames it Triceratops three-horned face. And remarkably, to his credit, he publishes a correction. He goes back and says, you know that giant bison alticornis? That was actually one of these. My mistake.
That's good science. You have to be willing to say, I was wrong. But once they knew what to look for, the floodgates opened, didn't they? This is where Hatcher really shines.
It was an absolute avalanche of fossils. Between 1889 and 1891, just the 3-year period, John Bell Hatcher went on an absolute tear in Wyoming. He collected 31 more or less complete skulls.
31 skulls in 3 years. That is an insane level of productivity.
It's staggering physical labor. You have to understand, these aren't chicken bones. A Triceratops skull with the surrounding rock matrix can weigh thousands of pounds. Hatcher and his team were digging these out with pickaxes and shovels, wrapping them in burlap and plaster, loading them onto horse-drawn wagons, and dragging them for miles across the Badlands to the nearest railhead.
And I've read that Hatcher basically destroyed his health doing this work, right? That the physical toll was immense.
He did. He worked himself to the bone, often in brutal conditions. But because he sent back this incredible wealth of material, this library of skulls, Marsh started noticing differences between them.
Differences like what?
Well, no two skulls were exactly alike. Some had slightly longer brow horns that curved upwards more. Some had taller, more fan-shaped frills. Some had a big, robust nose horn. Some had virtually no nose horn at all, just a little bump.
And because this was the 1800s, and the race was on to name as many new species as possible.
Marsh went naming crazy. He was a classic splitter. If it looked slightly different, he gave it a new species name. He named Triceratops elatus, Triceratops flabellatus, Triceratops calicornis, Triceratops serratus. I think he named something like 8 or 9 species in just a couple of years.
And this really sets the stage for a debate that, honestly, we are still having today over a century later. Are these all different species living side by side, or is it just one animal that changes shape as it grows and ages?
That is the central question of Triceratops science. But before we can even get to the shape-shifting, we need to understand the baseline. We need to build the beast. If you are standing next to a fully grown Triceratops horridus, what are you looking at?
You are looking at a biological tank, a meat mountain.
Laughs, that's an accurate description.
The sources consistently put them at 8 to 9 meters long. That's 26 to 30 feet. And weighing anywhere from 6 to 10 metric tons. Some estimates go even higher, up to 12.
To put that in perspective for everyone, that's the size and weight of a very large African bull elephant. But it's lower to the ground, much bulkier, more powerfully built.
And a huge chunk of that size, a disproportionate amount, is just the head.
It has one of the largest skulls of any land animal in history. The skull alone can be 2.5 meters long. That's over 8 feet.
8 feet. For just the head.
Just the head. So think about a standard doorway in your house. The entire skull wouldn't fit through it lengthwise. It's longer than your doorway is tall.
I can't even process that.
Yeah.
The head is almost a third of the entire animal's length. How does that not just tip over? How do you even lift that?
Massive, massive neck muscles and a very specific skeletal structure to support it. The first few vertebrae of the neck, the cervical vertebrae, are actually fused together into a solid block of bone called a syncervical.
Ah, like a handle.
Exactly. It creates a rigid, powerful attachment point for the enormous ligaments and muscles needed to swing that head around. But let's look at the business end of that skull, the mouth.
It's got that beak. It looked like a giant parrot beak, but on a rhino.
Yes, the rostral bone at the front. It's narrow and very deep, which means it was incredibly strong. This wasn't for delicate nibbling. This was for grasping and plucking huge bunches of vegetation. It would have been covered in a sharp keratin sheath, and it could probably snap through cycad trunks or thick branches with ease.
But inside the mouth, behind the beak, it gets even weirder. They didn't have molars for grinding like a cow, right?
Not at all. They had something far more complex and efficient. We call them dental batteries. This is just fascinating biological engineering.
Okay, break that down for me. What is a dental battery?
Imagine on each side of the jaw, you have 36 to 40 columns of teeth, all packed tightly together to form one continuous cutting surface.
Okay, a wall of teeth.
A wall of teeth. But in each of those columns, there were 3 to 5 teeth stacked vertically, one on top of the other inside the jawbone.
Stacked, like Pez dispensers for teeth.
That is the perfect analogy. As the top tooth, the one in use, wore down from chewing tough plants, it would fall out, and the next one in the column would have already moved up to replace it. It was a constant conveyor belt of new, sharp teeth.
So how many teeth are we talking about in total?
At any given time, you could be looking at a total of 432 to 800 teeth packed into that mouth.
That is a lot of teeth for an herbivore.
A huge number. And the way they worked was unique. If you watch a cow chew, they grind their food side to side. Triceratops didn't do that. Their jaw mechanics meant that the teeth slid past each other vertically in a high-angle shear.
So they weren't grinding the plants to a pulp, they were slicing and dicing them.
Exactly, like a set of self-sharpening scissors or biological garden shears. They were processing huge volumes of fibrous plant material, palms, cycads, tough ferns. These are not easy plants to eat. They were like living wood chippers.
Okay, moving back from that incredible head, we have this massive, robust body. And there was a huge debate for a very long time about how they actually stood, how they held up all that weight.
The four-limb debate. Yes, this is a classic in paleontology. If you look at the old paintings, the famous murals by Charles R. Knight from the early 1900s, Triceratops is shown with its front legs sprawled out wide to the sides, almost like a lizard or a crocodile.
Like it's in the middle of a push-up, permanently.
Right. And the logic at the time was that the head was so absurdly heavy, they needed that wide, stable base of support to keep from toppling over.
There's always a but.
But the biomechanics, the skeletal reconstruction, and most importantly, the trackways, the fossilized footprints they left behind, they all tell a different story. The current consensus is that they had an intermediate stance.
What does that mean, intermediate?
It means the hind legs were fully upright, columnar, right under the hips, like an elephant's. The front limbs were also mostly upright, but the elbows were slightly bowed out to the sides. It's not a full sprawl, but it's not a perfectly straight pillar either.
So more like a modern rhinoceros than a lizard.
Much more like a rhino. They were active, capable walkers. They weren't just lumbering, sprawling beasts. But their hands were weird. They retained a primitive condition.
Primitive how?
Well, if you look at your own hand, you can rotate your forearm so your palm faces down. That's called pronation. Most quadrupeds do this. Triceratops couldn't, or at least not fully. Its hands were semi-supinated, so its fingers pointed out away from the body.
So it's walking with its hands turned out permanently. That seems awkward.
It does to us, but it clearly worked for them. And it gets weirder. It only walked on the first 3 fingers of each hand. Those had hoof-like claws. Digits 4 and 5, your ring and pinky fingers, were vestigial. They were just little nubs that didn't even touch the ground and had no claws.
It's amazing the level of detail we can get from just the bones. But recently, we've been getting incredible details about the stuff that covered the bones. Let's talk about skin.
This is really exciting stuff. For 100 years, we just assumed leathery, elephant-like skin. It was a default guess. But in 2002, a specimen was found in Wyoming, nicknamed the Lane specimen.
And this one is special. It has skin impressions.
It does. It's preserved via a very rare process called clay templating. Basically, after the animal died, bacteria formed a slimy mat over the dead body. Clay then settled on top of that mat, creating a perfect, high-fidelity mold of the skin texture before everything rotted away.
So what does it look like? Is it just scaly?
It has large hexagonal scales, of course, that's the base texture.
Right.
But in the center of some of the larger scales, particularly on the back and tail, there are these conical projections, like little nipples or bumps rising up out of the middle of the scale.
And what does that imply? Why is that significant?
Well, in modern animals, and especially in other dinosaurs like Psittacosaurus, which is a very early, distant cousin of Triceratops, structures exactly like that are known to be anchor points for quills or bristles.
So, a fluffy Triceratops. A porcupine dino?
Maybe not fluffy like a kitten. Think more like the sparse, thick bristles on a wild boar or the quills on a porcupine. It completely challenges that classic image of a purely scaly reptilian tank. It might have been a spiky, bristly tank.
Which honestly somehow makes it even scarier.
It adds a whole new texture to the animal that we missed for over a century. It's a fantastic reminder that there's always more to learn.
Okay, let's get to the main event. The part everyone knows, the headgear. The 3 horns and the giant frill. Why? What is the point? Why invest so much biological energy in growing these massive, heavy bone structures?
This is the million-dollar question, and there isn't one simple answer. We have 3 main theories that all probably play a part.
Let's start with Theory A, the one we all learned as kids. Defense against predators.
The weapons theory. They evolved these horns to fight off hungry predators like Tyrannosaurus rex. And unlike some childhood myths, This one actually holds a lot of water. We have hard, direct evidence for this.
The smoking gun, or the smoking tooth mark, I guess.
There is a famous Triceratops specimen that has a partially healed bite mark on its brow horn. The spacing of the punctures, the shape of the marks, they match Tyrannosaurus teeth perfectly.
So a T-Rex literally bit this thing on the horn.
Bit it and broke it. But here's the crucial part of that story. The bone shows signs of healing. There's callus formation around the break.
Which means the Triceratops survived the encounter.
Exactly. It fought a T-Rex, took a bite to the face, and lived to tell the tale. We also see healed puncture wounds on the squamosal bone, that's the side part of the frill, that also match predator bites. So yes, they absolutely used these horns to defend themselves, and they were effective.
That is just so satisfying to know. The epic battle of the giants was a real thing. But what about Theory B, the Civil War? Did they use these weapons on each other?
Intraspecific combat. Fighting for mates, fighting for territory. For a long time, this was just speculation. It made sense. Modern horned animals do it. But then came the specimen known as Big John.
Big John. Sounds like a wrestler.
Might as well have been. Big John is a massive Triceratops specimen, one of the largest ever found. And he has a very distinct keyhole-shaped hole in his frill. It's a traumatic puncture wound. And when you analyze the shape and size of that hole, it is a perfect match for the tip of another Triceratops's brow horn.
So he got stabbed in the head by another Triceratops.
He did. And again, just like the T-Rex bite, the bone around the hole shows signs of healing. So this wasn't necessarily a fight to the death, but it was violent. They were locking horns and wrestling, and sometimes they missed and stabbed each other in the face shield.
Is that a one-off, or is it common?
It seems to be pretty common, and there was a statistical analysis done that looked at a large sample of skulls. They found that about 14% of Triceratops skulls have these kinds of traumatic injuries on the frill and face.
14%. 1 in 7. That's a high injury rate. That suggests this was a regular part of their lives.
It does, and what's really interesting is when they did the same analysis on Centrosaurus, another type of horned dinosaur with different horn arrangements, they didn't find those kinds of cranial injuries, which suggests Centrosaurus may be fought by flank butting or body blows, while Triceratops was specifically engaging in head-to-head combat, locking horns.
Like modern deer or antelope do today.
Exactly. But then that brings us to Theory C, the display theory. Maybe it's not all about violence.
This is the idea that the frill is basically a giant billboard.
Right. Think about that frill. It's a massive surface area of bone. We know from grooves on the surface that it was covered in a network of blood vessels.
So it could have been flushed with blood.
It could have been flushed with the blood to produce vibrant colors. Red, blue, complex patterns. It was very likely used for sexual selection males, showing off their big, colorful frills to attract mates, or for species identification. A way to say, hey, I'm a Triceratops, you're a Triceratops, let's hang out.
But there's a complication with the sex appeal only theory, right? And it has to do with the babies.
A very good catch. Yes, studies of juvenile skulls, some of them very small, show that the frill and horns start developing very early in life, long before the animal is sexually mature. If the frill was only for attracting a mate, you wouldn't expect a toddler Triceratops to be investing all that energy into growing one yet.
So it's probably a mix of all three. It's not one or the other.
Almost certainly. Evolution is thrifty. If you have a giant, metabolically expensive structure on your head, you're going to use it for everything you possibly can. Species recognition, defense against predators, wrestling with rivals, showing off to mates, and maybe even thermoregulation, pumping blood into it to cool down on a hot day.
A Swiss Army knife of a face.
A Swiss Army face. I like that.
Okay, speaking of faces changing over time, we need to talk about the shape-shifting. Because this is the part of the deep dive where the science gets really, really trippy and controversial.
This is where we enter the modern era of Triceratops research, largely driven by the work of Jack Horner, Mark Goodwin, and John Scannella.
And it starts with ontogeny. Ontogeny just means growth, right? The study of how an animal changes from a baby to an adult.
Exactly. In 2006, Horner and Goodwin published a landmark study. They looked at a growth series of Triceratops skulls from tiny melon-sized baby skulls all the way up to the massive adults. And what they found was that the animal undergoes a radical transformation as it ages.
It's not just getting bigger, the whole head is changing shape.
Completely. When a Triceratops is a baby, its little brow horns are just short, straight nubs. As it grows into a juvenile, the horns actually elongate and curve backward over the frill.
Backward.
Yeah.
But every toy, every movie has them pointing forward.
That's the adult form. As the animal hits adolescence, something incredible happens. The horns stop growing backward, the base of the horn remodels, and they reorient themselves to start growing forward and upward.
That sounds painful. How does that even work?
It involves a lot of bone resorption and redeposition. It's a very dynamic process, and as they become adults, the horns eventually hollow out at the base, probably to save weight. But the biggest change, the one that sparked the big controversy, is what happens to the frill.
And this leads us directly to the biggest debate in recent dinosaur science, the Torosaurus debate.
The Torosaurus debate. Okay, some context is needed here. Torosaurus was another dinosaur identified way back in 1891 by Marsh, right alongside Triceratops. It looks very, very similar. 3 horns, big frill, but with 2 key differences. It has a much longer, more elongated, almost rectangular frill, and that frill has 2 large holes in it. 2 big windows called fenestrae.
Whereas Triceratops is famous for having a relatively short, solid frill. No holes.
Correct. For over 100 years, everyone agreed. Triceratops is one species, Torosaurus is another. They were cousin species, maybe living in the same place at the same time, but distinct animals.
Until 2010.
Until John Scannella and Jack Horner published a paper with a bombshell hypothesis. Torosaurus does not exist.
Excuse me, what do you mean it doesn't exist? We have the skulls.
They argued that Torosaurus is not a separate species. It is simply a very, very old, fully mature, geriatric growth stage of Triceratops.
So Triceratops is the teenager and the adult, and Torosaurus is the grandpa.
That is exactly their argument. Their hypothesis is based on this idea of metaplastic bone. The bone of the frill isn't like cement, it's living tissue that can change throughout an animal's life. They argue that as a Triceratops gets really old, past what we'd consider a prime adult, its frill keeps lengthening and flaring out. To keep it from getting ridiculously heavy, the bone thins out in 2 specific spots, and eventually those spots resorb completely, opening up into the holes we see in Torosaurus.
That is a wild theory. What was the evidence they presented?
Well, their primary line of evidence was demographic. They pointed out that we find lots and lots of juvenile and subadult Triceratops, but we have never, ever found a confirmed juvenile Torosaurus.
That is suspicious.
Yeah.
Very suspicious.
It is. If Torosaurus is a real breeding species, where are its babies? Where are the teenagers? All the Torosaurus specimens we have are huge, mature animals. They also pointed to a few intermediate specimens, skulls that look like they are halfway between the 2 forms, with thinning bone where the holes would eventually open.
So case closed. The textbooks need to be rewritten. Torosaurus is dead.
Not so fast. This is science, we love to argue. Other paleontologists, people like Andrew Fark, Nicholas Longrich, Daniel Field, they push back hard.
What's their counter-argument? Where are the holes in the theory, so to speak?
They have several counter-arguments. First, they argue that some of the known Torosaurus specimens actually look skeletally mature in their bone texture, suggesting they weren't fully grown yet, which contradicts the geriatric stage idea.
Okay.
And conversely, they've found some absolutely massive Triceratops skulls that look extremely old. The bones are fully fused and rubbed, all the signs of old age are there, but they still have the classic, solid, short frill.
So if Triceratops is supposed to turn into Torosaurus when it gets old, why are there these really old Triceratops that haven't turned yet?
Exactly. That's a major sticking point.
Mm-hmm.
And finally, they argue that the proposed mechanism, the bone growing, then thinning, then opening holes, is an unprecedented and incredibly complex transformation that we don't see in any other known animal.
So where do we stand on this today? Is it 50-50?
It's still a very active debate. The consensus has not fully landed on one side. There was a more recent study in 2022 by Mallon and others that argued they have found subadult Torosaurus specimens, which, if true, would be strong evidence that it's a real separate species. But the shapeshifter idea, regardless of whether it's right in this specific case, has fundamentally changed how we look at all dinosaurs.
How so?
It's forced us to accept that we can't just assume a different shape means a different animal. It might just be a different age, or even a different sex.
It makes you wonder how many other dinosaurs in the museum are just distinct ages of each other.
Jack Horner has famously estimated that up to 1/3 of all named dinosaur species might just be growth stages of other known dinosaurs. We might be vastly, vastly overestimating dinosaur diversity.
That blows my mind. The implications of that are huge.
Okay.
Okay, let's step away from the bones for a minute and look at the world they actually lived in. Part 5, Life in the Late Cretaceous.
We are in Laramidia. This was an island continent. During the Late Cretaceous, a shallow sea called the Western Interior Seaway split North America in 2. Laramidia was the western strip, what is now Montana, Wyoming, the Dakotas, Alberta.
And the environment itself, what would it look and feel like?
Humid, subtropical. You should be thinking of coastal floodplains, swampy forests, meandering rivers. Think Louisiana or the Florida Everglades, but the trees are conifers, ferns, and early palms.
And based on the fossil record, if you were to take a walk through that forest, you would essentially trip over a Triceratops.
They were unbelievably abundant. The paleontologist Robert Bakker, who is another famous and colorful figure in the field, estimated that at the very, very end of the Cretaceous, in the ecosystems preserved in the Hell Creek Formation, Triceratops made up 5/6 of the entire large dinosaur fauna.
5/6, that's more than 80%.
It's overwhelmingly dominant. It's an ecosystem completely controlled by this one mega herbivore. The famous fossil hunter Barnum Brown once claimed he saw 500 Triceratops skulls in the field in a single season. They were the bison or the cows of the Cretaceous, at least in terms of their sheer numbers.
So were they social like cows? Did they live in big herds?
That's the tricky question. The evidence is ambiguous. We usually find their remains in isolation. A single skull here, a partial skeleton there. We don't have those massive bone beds of thousands of Triceratops all dying together like we do with some duck-billed dinosaurs.
So they were probably loners.
That was the traditional view, mostly solitary. But there are a few tantalizing exceptions. There is a fossil site in Montana that has the remains of 3 juveniles preserved together, maybe a little youth gang. And another site in Wyoming has 3 individuals of varying sizes, a large one, a medium one, and a small one found together, perhaps a small family unit.
And there's that one specific pathology you mentioned earlier.
Oh, the stepped-on tail. Yes. There's a Triceratops vertebra from the tail that shows a healed crush injury, the best explanation anyone has come up with. Another Triceratops accidentally stepped on its tail.
Which implies they were walking close enough together to step on each other's tails.
Exactly. So the current thinking is maybe they lived in small family groups or had loose associations, but probably not those thundering herds of thousands that you see in movies.
Now, you mentioned the environment was warm and subtropical. Let's talk metabolism.
Yeah.
Was Triceratops warm-blooded like a mammal or cold-blooded like a lizard?
The great metabolism debate. This seesaws back and forth constantly in paleontology. For a long time, the idea of gigantothermy was popular. The idea that they were so huge, they just stayed warm by retaining heat.
Like a giant living pizza stone, it takes all day to cool down.
A perfect analogy. But a very recent study in 2022 by Jasmina Wayman and her colleagues looked at the chemical signals of metabolism preserved in the fossil bone, and their results suggested that Triceratops might have been ectothermic.
Cold-blooded, a 10-ton cold-blooded animal.
Or at least having a much lower metabolic rate, more similar to modern reptiles than to birds or mammals, which is really weird because all the evidence suggests their earlier, smaller ancestors were warm-blooded.
So they might have evolved back to a slower metabolism. That seems counterintuitive.
It's possible. If you're a giant animal living in a warm, stable climate, generating too much of your own internal heat can actually be a problem. You risk overheating. So maybe for an animal this big, slowing down the internal furnace was actually a selective advantage.
Just lounging in the ferns, soaking up the sun, and eating palms.
Eating a lot of palms. And this leads to a really cool ecological detail: niche partitioning. We know for a fact they lived alongside another giant herbivore, the duck-billed dinosaur Edmontosaurus.
Right, so you have 2 massive plant eaters in the same forest. How did they not just eat all the same food and starve each other out?
Isotope studies of the enamel in their teeth give us the answer. The different chemical signatures show they were eating different things from the same environment. Triceratops, with its powerful beak and shearing teeth, was eating tougher, lower-growing vegetation things like ferns and cycads. Edmontosaurus, with its broader beak, was likely browsing on softer plants or things that were slightly higher up. They split the menu.
Nature always finds a way to pack more species in.
It really does.
So let's bring this incredible deep dive in for landing. We started with a bison mistake. We went through the wild story of the cowboy and the lasso. We built this biological tank with a parrot's beak and garden shears for teeth. We covered the epic battles with T-Rex, the brawls with each other, and the mind-bending idea of a shape-shifting skull.
It's an amazing journey. From a few fragmentary horns to a complex, living, breathing animal that dominated its world.
What's the single biggest takeaway for you? When you think of Triceratops now, what's the image that comes to mind?
For me, it's resilience. This
Yeah.
was one of the last ones standing. It evolved to be unbelievably robust, to be adaptable. It survived predator attacks that would kill almost anything else. It survived brutal injuries from its own kind. It so thoroughly dominated its landscape that it made up the vast majority of all large animals. It's the ultimate survivor. Right up until the day survival was no longer an option.
And for me, it's the mystery that's still left. The Torosaurus question is still unresolved. We're still debating about the bristles. We're still piecing together its social behavior. Even with hundreds of skulls, we are still arguing about the fundamental nature of what it actually was.
And that's the beauty of paleontology, isn't it? The past is never a closed book. There's always another fossil, another discovery that can change everything.
Here's my final provocative thought for you, the listener, today. We talked early on about how Triceratops is used to define the entire group Dinosauria. It's one of the two anchors, binding the mighty Triceratops to the modern songbird.
Yes, the two killers of Dinosauria.
But think about that shapeshifter concept again. If Torosaurus, an animal that looked different enough to be named a separate species for 100 years, is just an old Triceratops, and if Jack Horner is even partially right that maybe a third of all dinosaur species are just different growth stages, I want you to reconsider the next time you walk through a museum. Look at the skeletons lined up in the hall. How many of those are actually unique species, and how many might just be the teenager version of the skeleton standing right next to the adult version?
It makes you look at the concept of biodiversity in a whole new way. Are we looking at a prehistoric zoo filled with hundreds of different species? Or are we looking at a combination nursery, high school, and retirement home for just a handful of very changeable ones?
A nursery and a retirement home. I love that. On that note, thanks for diving deep with us today. Keep asking questions and keep looking at the bones.
And please don't lasso the fossils.
Please do not lasso the fossils. We'll see you next time.